Okay, let us wait for 2, 3 minutes and then we will start. So today we will do a new, we'll start a new chapter known as the Laplace equation. Okay. So before that, I will do some preliminaries. So I have asked you to have a look on the measure theory, basics of measure theory that will be required in this chapter. Okay. So I will do that. Yeah, Manish, you want to say something? Yes, Manish, go ahead. Hello, Manish.
No sir, ये वैसे ही हो गया था sir.
Oh, okay, okay, ठीक है. Okay, no problem. Okay. Okay, so let us start with a new chapter. So let me start. It's very slow today. Are you able to see the whiteboard? Yes.
Yes sir.
Okay, so it's a new chapter. We call it the Laplace equation. You know what is the Laplace equation? Means Laplacian of u equal to f of x. This is our main motivation to study. Okay, Laplacian of u equal to f of x. We will see what is f, what is u, and all those things in Rn or in some bounded domain or something. We will see. So this is the main aim. So let us today we will only do the preliminary. Lots of preliminaries we require. Okay, let us do it first briefly. Let us do it. So how to do first? Let us start with this one. Just I want to check whether you know all those things or not. Suppose I want to do the integration. How to do this? Anyone? Hmm? How to do integration? How to do this integration?
Uh, by replacing lower limit by t and limit t tends to 0.
So now you are grown up. So you know what is the you know this Morton convergence theorem, Fatou's lemma, dominated convergence theorem. In terms of that, you can tell like this, right? So this is a by definition. If the limit exists, we can write it like this. Right? This I can write as like this. This also, in other words, I can write n tends to infinity by monotone. Just 0 to 1, characteristic function of 1 by n infinity 1 by root x d. Yes or no? This I can write. This equal to this. Yes or no? Now monotone says that the limit will so this is nothing but by Morton convergence theorem, this is 1 by root x dx. Now you can compute this because this is a very nice integration. This is a Riemann integrable function, characteristic function of 1 by n comma infinity to 1 by x. Sorry, 1 by n comma 1. Whatever, yeah. Characteristic function of 1 by n to 1, so 1 by root x dx. So this you can integrate and do this. So if this limit exists, if this limit exists, then we compute the integral. In compute 0 to 1, 1 by root x dx. Just by this rule. Just using Morton convergence theorem, you can write that this is nothing but characteristic function 1 by n 1. So you know why, what is the Morton? Fn is your, this is your fnx, is characteristic function of 1 by n 1, 1 by root x. So is this a Morton function? Yes or no? Yes or no?
Oh, yes, sir.
So by using this Morton convergence theorem, we can so Fn converges to F, and also there is a Mortonicity. So you know that integration of Fn is equal to integration of F limit. Okay. So you know how to do this, all these things. Or now you tell me.
So, sir, before proceeding, can I ask some doubts from the
Yeah,
previous lecture?
yeah, sure.
So in the previous lecture, The last theorem was Holmgren's theorem, which
Yes.
said, so when we were trying to prove the Cauchy-Talon theorem for
Covariance.
higher order derivatives,
Uh, uh.
so we extracted a C infinity solution, a
No,
real analytic solution.
real, not C infinity. Don't confuse with C infinity. Always say real analytic, because C infinity functions are not always real analytic. The other way around is always true. Any real analytic functions are C infinity. Now tell me.
Yes, sir. So
Huh.
I mean, so the theorem, the last theorem says that when the equation is linear,
Huh.
then then the solution will be a real analytic only.
Yes, you provide exactly.
Under the given constraint that all the parameters are real analytic.
Exactly. You understand? Because it might, I said that Cauchy-Kovalevsky says that the real analyticity holds uniqueness of the real. There is a unique real analytic function. This does not say that there might not exist any CM solutions, right? It might be
Yes,
possible, right?
yes,
I said that the uniqueness holds only in the class of real analyticity. You understand? I have asked you to prove why if the functions are real analytic, why there is why real analytic solutions are unique. That you have to tell me why. So I have asked you. So the question is, the uniqueness is guaranteed in the class of real analytic functions, right? So it
yes.
does not tell you that it might possible that PDE has that PDE has some CM solution or C infinity solutions which are not which are not smooth. Sorry, which are not real analytic. But the Holmgren's uniqueness theorem says that it is not possible if your PDE is linear. You understand? That's
So,
all. Yes.
so there can be C infinity solutions which are not
Yes.
real analytic,
Yes. Yes.
even if the
If it
constraints
is not, if it is not, there are
linear.
example. I can give you an example in some book. You can see if they are not linear PD. Okay, Deepak.
Okay. Yes, sir.
Yes, that's the point. Good. So this is one point. Now you tell me
And
how
and
to.
and one more thing, sir. When we were trying to prove the theorem for in the higher order derivatives, then
Mhm.
uh, what you said that you can write the I mean you can put all.
In a system of first order PD.
Yeah, but you can change it into a system of first order
Yes.
PDEs,
Yes.
and from using
Then
the equation, you can take. Given the condition that A 0 0 k is not equal to 0, so
huh,
you can take divide it by this, and it would
exactly.
make sense.
Mhm.
But even if we do so, then the variable which is with respect to which we are calculating the derivative, the x
Uh-huh.
and variable, it will still be there in the function,
I
won't
did.
it?
I did not get you. Uh-huh. It's
I'll mail this one to you, sir. I don't think I will be able to explain. I'll mail this one to you.
okay.
Right?
Okay. Sure. Thank you. Mhm. Thank you. So now this one, this integral. When this integral is infinity. When? For which alpha? Quickly do it and tell me. Quickly.
When alpha is greater than 0 or greater than 1.
No. Quickly do it. What you have to write? Again, you just use that one. Epsilon 1 by x to the power alpha dx. So I'm not writing that. So x to the power minus alpha plus 1 to epsilon. So minus alpha plus 1 should be, because should be as epsilon tending, I will let epsilon tending to 0, right? So when alpha, clear? Yes or no? Yes or no? That is
Yes, sir. Yes, sir.
because you have to write epsilon to the power. This will means this is epsilon to the minus alpha. This is integrable when epsilon when minus alpha plus 1 is greater than equal to 0, you can say. So this one. Okay. So this is very important. So this is if and only if alpha is less than 1. Now tell me this, what will happen for this one? Huh? Do it and quickly tell me.
A alpha will greater than 1.
Strictly greater than. Alpha is strictly greater than. You know, you just integrate like limit r tending to infinity, that you can write 1 to r, or you can write in that Morton convergence theorem, right? So it will be again r to the power minus alpha plus 1 will come. So this is r tends to infinity, this should be minus alpha plus 1 should be less than 0, and so this is alpha is greater than 1. Okay, these are the small things, but I will use a lot. Just now I will tell a Lebesgue measure. A is a subset of R. I denote, this means denotes Lebesgue measure of A. Okay. So what is this? What is the Lebesgue measure of A plus x naught?
Lebesgue measure of A.
Very, very good. What is Lebesgue measure of this?
Mod of lambda times the Lebesgue measure of A.
Very good. Now suppose I give you Lebesgue Rn. Then what is A plus x naught?
Again, same.
What happened? Just a minute. And what is this?
This is mod of lambda raised of n into Lebesgue measure of A.
Mod of lambda?
Raised to power of n
Exactly.
into Lebesgue measure of A.
Yes, good. This you know. Now I will. So do you know convolution? Anyone knows? In measure theory, did you done this? Convolution? This one. Have you heard this name? Have you heard this? Yes or no? Tell me. एक हाँ या ना बोल दो just. पता है आपको? Yes, you know?
No, sir.
Okay, I will define. Just now, it is very important concept. Okay, try to give your attention, please. Are two functions. Okay, I will tell you what type of functions these are. Just first you consider two functions. Okay. Now I define an operation convolve with G. So this is a new function. F convolve. This is the term convolution. So F convolve with G. This is a function. How it is defined? I define it like that. Okay. F of y, g of x minus 1. So this definition is makes sense whenever this integral RHS exists. Clear? Is that clear? I define it. There are two. Let's take any two functions. You don't know. It's maybe measurable. Let's do two functions which are measurable. Okay. Okay. So I take the two functions, two measurable function, and I do the convolution. You know what is the meaning of an integration for a measurable function. So the integration like this: f of y. You just see, look it carefully. F of y, g of x minus y. I translate x minus y dy. This is a definition. Okay. Now I say that these make sense. This definition is well defined whenever this integral makes sense. What does it mean? The way the integral is less than infinity. Clear? The definition is clear. So f convolve of g is a new function we call h. Let's say h of x, how it is defined? Through the integral of fy g of x minus y dy. Okay, it's a very important operation in analysis. Okay, this convolution. So if you do further research in analysis like PDE, harmonic analysis, differential geometry, whatever you will do, these operator will come every time in your life. Okay, this convolution operator. Okay, this is called convolution. Yes, people will say convolution. Okay, so f convolve with g. Now you tell me immediately, who will tell me what are the sufficient condition I can put on f and g so that this integral makes sense? Quickly. Huh? Quickly. So today I will do all the preliminaries. So don't worry. Whatever in your mind, tell me. Whatever you think, you tell me. Hello, can you hear me? Hello, can you hear me?
Yes, sir. Yes, sir, we can hear you.
Just
Yes,
tell me.
sir.
Just look at the integral and tell me what condition I can impose on f and g so that this integral is less than 5. So you understand what is the meaning. So f convolve I mean is this. So I said that this is a well-defined definition whenever the right hand integral makes sense. Is that clear? Whenever right hand integral makes sense, means when I do the integration, these two integration, this integral is finite. Now my question is, just tell me which are the very simple function f and g when this integral is finite. Just tell me.
We can assume one function to be bounded and another, like that another will have it integral over R to be convergent.
Exactly. Very good. Excellent. Excellent. So that is called that what he said. Suppose if I consider one function is bounded and another function, the integral of this is finite. Okay. If and what is called if f is in L1. What is the meaning of f is in L1? You know this as I guess you know, right? F is in L1. You know.
Yeah, yes.
F is in L1 means if and only if integral f over R d phi is finite. Then we call f is in L1. Okay. So you more generally it is called LP if this pth norm is finite. You know all those things. Okay. So don't bother about P now. Just take and you take G to be bounded. That is norm of G, supremum norm you say. You know L infinity norm? Have you heard this name? L infinity norm? L infinity norm. Have you heard this name?
Yes, sir.
Okay. So when L infinity norm is or G is in L infinity. Okay. Then this integral makes sense. Why? Just see. There is some problem. Okay. F of y, g of x minus y dy. These integral have to make sense. So I take the modulus. Okay. This is nicely mod of fy, mod of g of x minus y. Sorry. Now we know that norm of g L infinity norm. You know what is the norm? It's less than c. So I can take less than norm of g L infinity. So this is f1, and we know that this is also finite. So this is sometimes writes like that. F1, which is finite. So this is less than norm of g infinity. So this is finite. So as you said, if we assume f is in L1 and g is in L infinity, then this integral makes sense. Very good. Okay. Now a very nice theorem. If f is in L1, suppose g is a C1 function. You know what is a C1 function? What is that? Tell me, anyone? And g prime is less than equal to. So the derivative of g is bounded. Okay. Then f convolution of g is also a C1 function, and f convolution g ka derivative is nothing but f convolution g derivative. Who will prove this? What you have to show? F convolution G is a C1 function. First of all, you have to show it's a derivative exists. Yes or no? Please tell me yes or no, Baba. Please.
Yes, sir.
Please, at least you should tell. This is very, very important concept. F of x plus h minus f convolution g of x. First of all, we have to check whether it's a. This I can write as limit h tending to 0. Just a definition. F convolution of g x plus h. What does it mean? F of y g of, if you write down, I write down the minus f of g of x plus h minus y minus g of x minus y. I'm writing these two together, okay? By h. Okay? Is that okay? Now you tell me why I can put the limit. The limit will go inside. Why? 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 Use this fact. Use this fact. Okay? And if I do this, this is nothing but fy. This is, what is this? What is this? What is this?
G prime
G prime of
x minus y.
this is equal to f convolution. Clear? Is that clear? This is important step. You should check this. Okay? Why this limit goes inside? Okay? You will check, right? You use your favorite. Which theorem you have to use?
Dominated convergence theorem.
Yes. And what will be your dominated function? F is an L1 function, and this you just in the interior you can do it using Lagrange mean value theorem. F prime G prime of Z into this one, right? Z prime of Z is less than or equal to M, right? So F is an L1 function. So that's done. Okay. You use dominated convergence theorem and the fact that okay. Now I will be doing a way. So the remark is, you see. So what is the why convolution is very important? You just see. F is a L1 function, not even a continuous function. You know, there are functions which are not continuous, right? L1 functions are not always continuous. You just convolve with a nice function. G is a C1 function. This is a rough, it might not be a continuous function, but this is a very nice function. This is a nice function. Nice function. Whenever you convolve with a G, this is a bad function. That means not a continuous function, bad function. Not always, right? So when you convolve with a nice function, this becomes a nice function. How nice is this? It can have a C1ness, right? This is a G. The function which is it takes the regularity of the nice. G is a C1, so F convolution G is a C1 function. Okay? So that this is the beautiness of the convolution. So one function is bad, very rough function. It can be very, very bad. And another is a nice function. If you convolve it, these two functions, it will be a very nice function. Okay? That is the reason. This is one of the reason that this is a very interesting operations. Okay? Now we will see. There is something called mollifier. I will define what is mollifier. Okay? So I define a function phi x, C, a constant, e to the power minus 1 by 1 minus mod x square. Okay? Whenever mod x is less than 1 and 0 whenever mod x is greater than equal to 1. And what is C? C is chosen. This constant is chosen to be chosen. This constant to be chosen such that integral of phi of dx equal to 1. Okay. So you can tell me how this constant C is chosen so that this integration of phi is 1. You know what is the meaning of that. Okay. Now you just look at the function C times e to the power minus 1 by 1. So as mod x is going to 1, where this function is going? At x mod x equal to 1, what is the value of this function? Hmm?
0, approaching 0.
Approaching 0. So at the boundary it is 0 then. How the function and what when mod x equal to 0, how it looks? What is try to draw the graph of this function. So this is your 0, this is let's say minus 1, this is 1. Okay. So the function at, so just look at it. At x equal to, so it is a decreasing function, one can see, and of course in both sides. So mod x less than 1, the function will be look like this. It takes the value peak at mod x equal to 0, then it comes at 1 and then it is 0. Is that clear? This is the function phi x. Is that clear? All of you? What is phi x? Again I am writing. Phi x is this, we have to understand. C e to the power minus 1 by 1 minus mod x square when mod x is less than 1 and 0 when mod x is. You can check, this is a very nice smooth function such that this happens. Clear? Is that clear? Yes or no?
Yes, sir.
Okay. Now you tell me, what is the support of phi x? You know definition of support? Do you know the definition of support? Support of a function?
Yes, sir.
This
Yes,
is the
sir.
autonomous set of all x belongs to just a minute, wait, R such that phi x is not equal to 0 and take the closure. The support is always a closed set. Okay. So what is the support of this function? This phi, particular phi, equal to, what is the support?
Closed interval minus 1 to 1.
Yes, that is minus 1 to 1. Or in a mathematical mode way, I can write, because I can do it for Rn also. Is that clear? Is that clear?
Yes, sir.
Now I define another function. Just see. Define phi epsilon x as 1 by epsilon to the power n phi of x by epsilon. This phi is the same phi. Same phi. What I have done? I have flattened it. X by epsilon, 1 by epsilon. Now you tell me, what is the support of phi epsilon for epsilon positive? What is the support of phi epsilon? Who will tell me? What is the support of phi epsilon?
Minus epsilon to epsilon closed interval.
Yes, very good. Why? Because you know that phi has a support in minus 1 to 1. Right? That means x by epsilon. This support means x by epsilon. X by epsilon should, the support of this one phi epsilon is the phi has a support x by, so x by epsilon should be greater than 1 minus 1. It means x should be greater than 1 epsilon. This implies the support of phi epsilon is Support is always a closed set, sorry. So minus epsilon to epsilon. Clear? So what am I doing? And also, this is important. What is phi epsilon x dx? Who will tell me? Who will tell me? This is equal to 1 by epsilon to the power n r phi of x, sorry, epsilon to, this is Rn, let's say Rn x by epsilon dx. Okay, so I should write this is as b0 epsilon, because this is not I am not doing in a in an interval. If I am doing in n dimension, that is why n comes. Otherwise, just I will take 1 by epsilon. This n signifies the dimension. Okay, Rn. Okay. Now you tell me what is that integral equal to? What I can write? X by epsilon I can write equal to y. So dy is, you use the scaling property, right? 1 by epsilon to the power n into dx. So these imply dx is equal to epsilon to the power n dy. Okay? So that means dx, that epsilon n, this epsilon n cancels out. This is Rn phi of y dy. And what is the integral of phi y dy? Huh? What is the integral of phi y dy?
1.
Exactly. So what am I getting? Integral over Rn, or you can say over R phi epsilon x dx is 1. Now you tell me, this is your minus 1, 1. This is 0. So when phi is like this, oh, sorry. I make a bigger picture, sorry. Just a minute, I can draw here. Minus 1, 1. So this is your phi epsilon, phi x. Now you just tell me, what will be the phi epsilon, how it looks like? So epsilon, let's say epsilon is less than 1. So you said that phi epsilon has a support minus epsilon to epsilon. But what is the integration? Integration, in other words, you can see as the area under the graph. And as I said, the integral is the same. So the function will look like this, because the area has to preserve, right? If this interval is small, then it has to go up, because the area has to be preserved, because the integral is 1. As epsilon goes to 0, the function is like that. As epsilon goes to 0, this p epsilon somewhere, I will not say what is that. It is going somewhere to this, concentrating at some point 1 at 0. Yes or no? This you have to understand or not? This is very important in rest of the course. So your phi epsilon is, if you don't like n, epsilon phi of x by epsilon. We have seen that the support of phi epsilon is minus epsilon to epsilon. That means smaller, but we know that integral of phi epsilon is 1. That means the area under that curve is the same. That means the function has to little bit above, because the breadth-wise it is small, it has to go up. So as we going epsilon becoming smaller and smaller, the peak will be go higher and higher. Is that clear or not? All of you?
Yes.
Clear? It's a very nice, right? Very simple arguments, but very nice, right? Okay. This is the beauty of scaling. You will see in the later courses or in the later research, the scaling plays a very important role in analysis or in geometry. Okay, this type of scaling plays a very, very important role. Okay, what I am doing, I am concentrating the function. Another scaling might possible that I can define like phi epsilon as this can also possible. Phi of x epsilon, instead of x by epsilon, I can define x epsilon. then the graph of the function will look like, it will flatten up. Okay, so these scalings will play a very important role in your life. Okay, if you do mathematics. Okay, so this is one type of, this is called modifier. This phi is called a modifier. Okay, clear. Now you will see what are the, why I am doing this modifier. Okay, you can say it's a theorem. Tomorrow the tutor will explain you better. So let's take let f is in L1. Okay, and you define f epsilon, a function I define like this. F convolve with phi epsilon. Phi epsilon is the same phi epsilon. It's smooth, so phi epsilon is the same. Is a C infinity function in R or Rn. It is a C infinity function with a support in, minus epsilon to plus epsilon. So this is a very nasty function, but this is a very smooth function, C infinity function. So what we'll expect for f epsilon? Then first is f epsilon is the C infinity of R. Okay, it's a very smooth function once we convolve with a modifier. Okay, so this is a part A. Part B says that if f is continuous, sorry, it don't require continuity first. F is a C infinity, and next point says that f epsilon converges to f almost everywhere. This is another beauty. This is f convolve with phi epsilon. So I say that f epsilon will converge to almost, because why it is almost everywhere? Because f, we don't know whether it is a continuous function or not. It is just an L1 function. So you cannot say that f converges to f for every point, because this function may not defined for every point, right? That is why almost everywhere comes. Okay, so I have to show that f epsilon converges to f almost everywhere. If f is a continuous function, see, if f is continuous, then f epsilon converges to f uniformly on every compact sets. Okay, is that okay? So this A, B, this C will prove, you will be later proved, or you can try, or the tutor will prove you. I will prove this, that f epsilon converges to f almost everywhere. Okay. So what is f epsilon? F epsilon as x is f convolve with phi epsilon x. What is this? This is R f of y phi epsilon of x minus y. This is a definition of convolution. And what is the definition of phi epsilon? This is nothing but 1 by epsilon. Just a minute. F of y phi of, just a minute. Of x minus y by epsilon t1. Okay, this is f. Now you have to show that f epsilon x converges to, as epsilon tending to 0, converges to f of x almost everywhere. That means outside a set of measures 0, this converges to f. Why almost everywhere case? Because of this reason. Because f may not be defined continuously. You know how to prove this. Please try to try. What you have to show? Tell me, anyone? Yes, how to do that? What you have to show?
Measure of the set such that this does not
Yes,
converge.
you have to show that for almost every x. For almost every x, this is, there is some problem today. F epsilon x minus f of x, I can make converges to 0 as epsilon for almost every x. Okay. Now recall a very important theorem. Recall Lebesgue differentiation theorem. Lebesgue. If you don't know, just at least differentiation theorem. Okay. If you don't know, just at least you should know the statement. Okay. Don't know. If sorry, let f is in L1 loop. You know what is the log function? You know what is L1 log? Yes or no? L1 log means for any compact set K, this integral is finite. It might possible that if over R it is not finite. But for every compact, so this is L1 log of R, means for every compact set in R, this integral is finite. So if I say that f is a L1R, then automatically f is a L1 log. But this is not always true. If L1 log does not imply f is in L1. You can have a very simple example. Okay. Just you take a constant function. Just take a constant function. Constant functions, the constant function is not so over R. A constant function 1 dx, it is infinity. But for every compact set, the constant function is, for every compact set K, 1 dx over a compact set is finite. Okay. So L1 log. Okay. So let f is in L1 log. Then this happens. Then limit R tending to 0, 1 by measure of the ball x of R, b of xr, f of y minus f of x. You fix some point x. So what is saying that you fixed a point x. Okay. You take the difference between fy minus fx. Okay. And y are inside the ball of radius xr. If you take the integral dy with respect to that and divide by 1 by bxr, this should go to 0. Now the point is, for which x this will go to 0? For almost every x in R. Rn, in fact. Is that clear, the statement? Let f is in a L1 log function. Then that says that then limit R tending to 0. So when you are squeezing, just draw a picture. So this is your x. You take b of xr. Okay. This is your R. Okay. So you take the difference f of y minus f of x. Take the modulus. So where is y? Y lies between inside the ball. Inside the ball, take the integral dy over the integral b of xr and divide by the measure of bxr. It should be right. Limit r tending to 0. This should go to 0. But this will go to 0 not for every x, for almost every x in R. In Rn or R, whatever. Now, the simple statement is, if f is a continuous function, then limit r tending to 0, 1 by bxr, b of xr, fy minus f of x, dy equal to 0 for all x in Rn. This continuity implies for all x. Can you immediately prove this for continuous function? Anyone? Can you see the proof immediately? Why this goes to 0? Can you see the proof immediately? If the function is continuous, you just think y as r going to 0, that means y going to x. So you can take mod of fy minus fx is a continuous. So when y is very close to x, r tending to 0 means you can always find a delta, right? Oh, sorry, for every epsilon we can always find a delta such that mod of fy minus fx is less than epsilon for all x is inside the delta. So you can take out fy minus x and supremum takes out, comes out, fy minus fx comes out, which is less than epsilon. That this will be so the remaining are the integral of bxr, which is a measure of bxr. This measure of bxr and this measure of bxr cancel. So this is less than epsilon. Epsilon is arbitrary. This proves that this goes to 0. Is that clear? If the function is continuous, your life is easy. Always this is true for all x in Rn. But for if f is in L1 log, then the proof is quite difficult. You have to use some covering lemma and all those arguments are needed to prove this. But then we will have a restriction that it will go to 0 almost every x. Is that clear to all of you? Yes or no? Yes or no? Yes or no? Shammi, Navneet, Kritika,
Yes, sir.
Anshu, Manish. Is that clear?
Yes, sir.
Yash, Ekans, Ankit. Huh? Meenakshi. Clear? Nikita, Sushil, Yash, Vishwa,
Yes, sir.
Annu.
Yes, sir.
Good, 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 good. So you can see the proof if it's a continuous. So life is quite easy if you are in a setting of continuous function. Okay. This is known as the Lebesgue differentiation theorem. Okay. This is something called Lebesgue differentiation. Very important theorem. Okay. Have you done this proof in your measure theory course? Huh? What happened?
No, sir.
Oh, okay, okay. But okay, and at least you can see the proof for continuous. So how can I give you this Lebesgue differentiation? So you should have done this Lebesgue differentiation theorem. Anyway, so there's a lots of application. Okay, good. Anyway, I will ask my tutor to prove the Lebesgue. I don't know whether they can prove. So what you want? You want the proof? Yes or no? Huh? You want to see the proof or not? What is your opinion? Or that's all? You just enough. You see that statement. What?
Yes, sir. True.
You want to see the proof? Maybe we can do it in the tutorial class. What you say?
Yes.
What happened? Others? Okay, we will see. Okay. Now I have to use the Lebesgue differentiation. So for almost every x, so for almost every x, limit r tending to 0, 1 by bxr for almost every x. Now you take from that x, that set for almost fix such x, fix such a point x. Just a minute. Fix such a point x. Then you understand what I mean to take such a point x. You understand, right? So that this happens. This f of x, this for almost every x, this goes to 0. You take one such x. Okay. Now you consider f of epsilon x minus f of x. You will see how this theorem will be used here. Okay. This is, so can you tell me what is this? Integral over? Can I write this? Huh? Can I write this? If yes, why? What I am writing, this fx, I am writing this fx phi epsilon x minus y dy. So fx is nothing, so fx comes out. And what is the integral of phi epsilon x minus y dy? It's a x minus y, you put z, translation invariant, this is Rn, whatever Rn. So this is 1. The integral is 1. This is nothing but fx. So I use that fact. Okay? Okay. So which is equal to 1 by epsilon to the power n, and the integral will be bx epsilon, because outside that it is 0. You just checked. You know why. X minus y by epsilon. So the what is the support? You know the support of phi is 1. So x minus y by epsilon should be lie between. So this will be right? So x minus y by epsilon should lie between b 0 1. This implies that y should lie between b of x epsilon. Okay, good. So this happens. So outside the modulus is there. So fi minus f of x. Okay. So this is less than equal to by epsilon to the power n bx epsilon px minus y by epsilon modulus fi minus fx. Okay. Is that okay? Is that okay? Yes or no? Okay, right? Okay. Now you tell me what I will do. What is the measure? Now tell me what is the Lebesgue measure I take of bx epsilon? Who will tell me? At least some order, some constant time something. What is the Lebesgue measure of bx epsilon? In n dimension, Rn. Because this, let's say this is in Rn. So what is the Lebesgue measure of a ball bx epsilon in Rn? Huh? This is equal to x plus Lebesgue measure of 0 epsilon, translation invariant. So this is Lebesgue measure of 0 epsilon. What is the Lebesgue measure of b0 epsilon? Rn. At least you take n equal to 2. What will be the Lebesgue measure of b0 epsilon in n equal to 2? Some order, some constant time, some. What is the? Huh?
Constant time sin raised to power n.
Yes, very good. Constant time epsilon to the power n. Okay. If it's n equal, you know, pi r square. What is the pi r b0 r? What is the two-dimensional Lebesgue measure of a ball? Pi r square, right? So square. I mean to say this radius to the power square. So for n dimension, this will be epsilon to the power n. Okay. Just using the Fubini, you can get it. Okay. So this you see, this is some order of epsilon to the power n, and this is a Lebesgue measure. So I can do a constant time c epsilon to the power n, so that this becomes the Lebesgue measure of this. Okay. Phi of x minus y by epsilon f of y minus f of x dy. Now you tell me, I can bound it if this is less than equal to 1 or not. Yes or no? Huh? Yes or no? For fixed epsilon. What happened? What happened? Some constant, yes or no?
Yes, sir.
Just check. You just check. This is less than equal to. So this is less than equal to this. You can write as 1 of bx epsilon. Bx epsilon. Okay? Is that okay? Because this is less than equal to 1. You can just think e to the power minus 1 by what is the maximum value it can take, x by epsilon. As epsilon goes to 0 also it can take x maximum value 1. So what is that? Now tell me. Now what I have to do, because I have chosen, now you just let, now what I have proved is the following, that if epsilon x minus f of x is nothing but 1 by some constant time bx epsilon fy minus f of x dy. Now letting epsilon tending to 0. I have taken x to be the point from the Lebesgue, where the Lebesgue differentiation holds. So this will go to that is where it will go
0.
this imply f epsilon x converges to f of x almost. This almost everyone counts because this point I have chosen, right? Such a point x. This is almost everywhere. So you have to take a zero set out where it is happens. Okay. So I have proved that f epsilon converges to f. That is f epsilon. I again recall f epsilon x is f convolution. Is that clear? Very simple. Clear? Is it clear?
Yes, sir.
Okay, very good. Now one more small thing I will tell you. Something else. So what, because if you see the, when I am defining f convolution gx, everything I have to define in R, right? Fy g of x minus y dy. Because this x minus, this translation should make sense because x minus y is any point in R. So if I fix some omega, if I do this, it will be might be a problem because this x minus y may not be a point in omega. You agree? In omega. Agreed or not? Because this translation should make sense. This is a translation. So since we are working in R, so no problem, right? Is that okay? Yes or no? Because x minus y should make sense, right?
Yes, sir.
Because
Yes.
it might happen that x minus y go outside the omega. Then there is no make sense, right? G is a function, let's say f and g become some functions in from omega to R, Then of course this x minus y should, if x minus y is a proper, we can do that. But in general, we cannot able to guarantee whether x minus y is in there. Now we just see. Suppose it's a very small remark, but very important remark. Suppose I work with omega to R. Omega is some open bounded set. Omega is some open set in R. Okay. The question is, can we define f convolution phi epsilon? This is important. Instead of any g, I want to define phi epsilon about it. So f convolution phi epsilon x is nothing but p0 epsilon f of x minus y phi epsilon y dy. You need x minus y. See, you need this x minus y. So how we will guarantee that x minus y belongs to b0 epsilon, right? Sorry, x minus y should belongs to b0 epsilon. In other words, I need y should be in bx epsilon. This is implied this. To make sense, x minus y should belongs to b0 epsilon. That means y should belongs to bx epsilon. Yes or no? Right? Okay. For that you define a set. I don't know whether you have seen such function set to define omega epsilon. X belongs to omega such that distance between x to del omega. X is a bounded set, let's say. So this is your x, this is your omega. Okay, and this is your del omega. What is the meaning of that set of what is how the omega epsilon will look like? Anyone? Omega epsilon says that distance between x and del omega should be greater than epsilon. For epsilon positive, I define a new set omega epsilon, which is a subset of omega, and such that suppose if your x is in del omega, so what will happen? What is the distance between x and del? Suppose x is in del omega. So what is the distance between del omega and del omega? X to del omega. Huh? You know, this is the distance, the infimum of x minus y, where y belongs to del omega. Suppose your x is itself in del omega. So the infimum is 0. That means distance is 0. This says that distance to x to del omega is always positive, always greater than epsilon. That means this is your set. This is the distance omega at least. So this is your omega epsilon. So you are strictly inside the domain. Now this is your omega epsilon. So you are omega distance away from the boundary. You are at least omega distance away from the boundary. Right? Now you just see. If you take x is in omega epsilon, then clearly bx epsilon is contained in omega. Agreed or not? Because maximum the x can go here. If x is here in your omega epsilon, you take an epsilon neighborhood bx epsilon, so it will be strictly inside omega. You agree? Because there is always a omega distance there. You agree? Clear? Yes or no?
Yes, sir.
So if you x is in omega epsilon, then bx epsilon is always this is true. Okay? And if this is true, then you can define this always makes sense. Is defined for x in omega. So not for all omega you can define, but you can restrict yourself inside some omega epsilon, then you can define f convolution phi epsilon. Okay, good. So that is for all convolution. So something more will be done in the tutorial. Okay, in the for the convolution. Okay. Now I will do little bit of polar coordinates. Okay. Polar coordinates. These are very useful thing in. So you should have done all these things in the measure theory, this convolution and all those things. You should have done in the measure theory course. So in measure theory course, if you haven't, you did not see this convolution. Young's inequality, convolution, you didn't see?
Yes, sir.
Huh?
No,
Yes or
sir.
no? Never. Yes or no? I'm not able to hear you. You haven't. You did not see.
No,
this?
sir, we have not seen.
You haven't seen.
No, sir.
But at least it is clear now, right? Little bit, Navneet.
Sir, I was saying that I've studied this in the differential geometry.
Okay. Okay. Yeah. Because PD, you will see later on. PD and PD. If you want to do some serious PD, you will require differential geometry, function analysis, and measure theory. These are the three subjects you require. And of course, harmonic analysis, that is a much higher level. But if you want to study a deep, at least an advanced course in PDE, you should know these three topics: differential geometry, measure theory, and lots of function analysis. Okay. Okay. Anyway, so this is called polar. Now we will do some polar coordinates. Okay. I have seen this. You also should have seen this, but unfortunately you haven't seen this. Fx dx. As I said, you can say Rn. You can write this. I don't want to make again the same comment that del b0r f ds. Is it clear why it is happening? You understand, right? Yes or no? At least intuitively you understand. As I said, just think of R2. You want to fill this with del b0r. Now take the union R equal to from, let's say, 0 to infinity. That will cover your Rn. Yes or no? This is roughly the polar coordinates. In R2, you know the polar coordinates. R dr d theta, R dr d theta. Okay, so same thing. Okay. Now you tell me what is the measure of B01 in Rn. I will compute this using this formula. Okay. You should have done all these things in measure theory. Anyway, so this is Rn. So what is B? This is a characteristic function of B01 x dx. This is your fx. Right? Am I right? Yes or no? Am I right?
Yes, sir.
Okay. Now what I will write? 0 to infinity. Now just suppose this holds true. Of course, this equality, you have to prove these polar coordinates. This is just this you can prove using Fuvini actually. Fuvini and change of variable formula. Okay. So characteristic function of B01 x dx. Clear? Okay. Now what I will do? Now I write down characteristic function of this one. So R is from 0 to 1. So if you see R when R is greater than 1, this does not make sense because this is 0, right? So you have to consider this plane only, this ball. This is B01. Outside, this is 0. So this I can write 0 to 1. Okay? LB0R characteristic function of 0, 1 x dx, because outside it does not make sense. From 1 to infinity, if I do 1 to infinity, this is 0 characteristic, does not make sense, right? Now you just see characteristic function of ball 0, 1. So this, sorry, ds dr, sorry, I should write now ds dr. So this is nothing but this is 0 to 1 del b0r 1 ds dr. Because at the boundary del b0r means r from 0 to 1, all over the function is constant. So on del b0r it is 1. Okay. Is that clear? This step is clear. Why I have written 1? Huh? Yes or no? Because the characteristic function of characteristic b01 is 1. So you are in ds is 0r, r is from 0. So it is some point inside the b01. So it is 1. Okay. So now what will happen? Now just see. Now what I will do, I will write sigma is equal to s by r. Okay, I will change the variable ds to d sigma. So, and this is a dr. So ds is a measure n-1 dimensional measure. Yes or no? How to explain it? Right, just a minute. Rn is, I am writing Rn as like this: 0 infinity cross Sn minus 1. sorry, SR, because I am writing list, right? This is called wrap product, so you don't have to understand this. So I'm writing Rn as 0, infinity, comma, infinity, cross sum SR. This is this measure is one dimensional measure, and this is n minus 1 dimension. SR. The sphere, this is a SR is a mod x equal to R. So this is a n minus 1 dimensional sphere. Yes or no? Yes or no? Yes or no? If you study differential geometry, this is there. Anyway, sigma is equal to S by R. So this S is actually on the sphere SR. So this is a n minus 1 dimensional measure. So d sigma will be 1 by R to the power n minus 1 ds. So ds is nothing but R to the power n minus 1 d sigma. Okay? So and what will be the now mod sigma? Mod S is R, because S is in del br. This is 1. So after change of variable, what I did, R to the power n minus 1 del b 0 1. So this is a d sigma dr. Okay. So this is a measure of a S1. This is a measure of S1, which is a fixed quantity. S1 is a sphere, n minus 1 dimensional sphere in essence. So mod x equal to 1. The measure of mod x is a fixed quantity, 1, because this is a Sn minus 1. This is Sn minus 1. You know what is Sn minus 1, right? So this we denote as Wn minus 1. This is just a quantity. Wn minus 1 is some fixed quantity. Okay. So this is nothing but Wn minus 1, 0 to 1, R to the power n minus 1 dr. If you integrate, so you will get Wn minus 1 by n. Clear? So this is nothing but the measure of ball is nothing but Wn minus 1 measure of sphere by what the measure of a ball of radius 1 is equal to, this is Wn minus 1 is the measure of a Sn minus 1 measure of it. Okay. And now you just think what will be n equal to 2 for n equal to 2? N equal to 2, what will be the n equal to 2? This is W1 by 2, and what is that is pi r square. R is 1, pi, so this is 1. So this is pi actually. So W1 is nothing but 2 pi in case of n equal to 2. Okay. This is the Wn minus 1 is the measure of a sphere, and B01 is the measure of a ball. So this is the measure of a ball. This is the measure of a sphere. So n dimensional measure is 0 of a sphere, but Wn minus 1 is a n minus 1 dimensional measure. You understand that point? Okay. Is that clear? Or it is not clear? Is that clear or not? Please tell all of you. Anyway, when I will do some example, it will be clear. Don't worry. So at least you should understand. This is nothing but, you understand, Rn I am breaking like 0 infinity some cross SR, right? So this is the main funda. Okay. Now I just recall integration by parts and then I will stop. Okay. This I have already done, but still I want to recall once more. Let omega be a bounded open set with, you know what is the meaning of a C1 boundary. Such type of thing I am excluding. on domain. Okay, then for every uv belongs to C1 omega intersection C omega closure, this holds. U del u by del xi v dx is equal to minus omega the del u del v by del xi. This I have done already. The boundary term. uv nu I d sigma, because the boundary measure is one dimension less than the omega measure. Okay, where this, please go through this integration by parts again. Okay, because this is very important. Nu x is nu 1x, nu 2x, nu ix, nu nx. Okay, with a unit outward normal. So unit outward okay, that's all. Okay, so just have a look on that. So today only we do a review. Okay, preliminaries which will be required in the course. So you should, again I am telling you, monotone convergence theorem, monotone, Fatou's lemma, and dominated convergence theorem. This please go through. Just go through once again the polar coordinates, what I have done today. Polar coordinates. This modifier you draw in with your hand again, this modifier function, and make yourself comfortable that this is actually this type of this thing happening. Like this, okay, and rest is polar coordinate, monotone, dominant, and the convolution. So I will ask the tutors to do it again, this convolution. Okay, more properties on convolutions tomorrow. More properties of convolution. Properties of convolution. Okay, with this this with modifier and all those things, so that you are comfortable. Is that okay? Anything else you need to understand? And Lebesgue differentiation theorem, we have done a new topic, new thing, a Lebesgue differentiation theorem. Just look at the statement, Lebesgue differentiation theorem. Okay, that's all. Okay, just come to next class. You just prepare these three, and rest I will do that. Okay. Okay. So anything else you want to ask me? I think now the course is.
So here, say C1 boundary means what?
C1 boundary means there is not kind of this type of
Kind of smooth boundary, kind of.
Smooth, yeah. Listen, there is no cusp. This is called cusp. There is a proper definition. I don't want to go to that proper definition. It will confuse you. This is called, this type of cusp things are not there. Okay. Okay. That's all.
So basically we are saying like we can parameterize our boundary.
Exactly.
With us.
Exactly. That means
Okay.
actually these boundaries are the n-1 dimensional manifolds. You can prove that. Okay. You have done a differential geometry course?
No, sir.
Okay. So these boundary actually are the manifolds. Okay, parameterized manifolds. Okay, so it's a very nice topic. So this is all. That's all. So you don't have to require. If you require, I will tell you if you want, if you wish. So that's all. So now we will see that the PD will be only with such type of things, this convolution, integration by parts, and all those things. Okay. So for you, I think this is you thought that PDE will be solving, right? Huh? Solving some partial differential equations, right? Yes or no? This is very counterintuitive to you, right? So this is something. So I did this fast order also. You can have some more geometry on it, but I did not do that because you don't know much differential geometry. So when I was in TIFR, so people started with the differential geometry. So they assume that they are in the first class, they start what is the manifold and all those things, and then they start with the this fast order PDE on manifolds. This characteristic surfaces, they call characteristic, not the surface, they call parameterized surface and all those things. And in n-dimensional, you have to use implicit and inverse function theorem there only. So that's a much general form. So I am doing in a very particular form. Okay.
So
Okay.
Laplace transform also work for solving PDEs.
No, we will see later all those things. This is not a solving course. So you are just, this PD is not, PD doesn't mean solve. So I do my research in partial differential equation. I never ever solve any PD. Okay. So solving, that means you have to have derivative and solve. This is an old fashioned thing. Okay. PD is a very rich topic. Okay. So it's geometry, measure theory, function analysis, and all those things. Combination of all these topics. Okay. Okay. Clear? So you will see now. Now the beauty of PDE, will see how this measure theory, Lebesgue differentiation theorem, change of variable formula, and all this will play a very beautiful role. Real analytic functions. Okay. Okay. Laplace transform also, there are deep things in Laplace transform. If time permits, we will do something. Okay. Laplace transform also. Anyway. Okay. Is that okay? So I work in this type of differential geometry and PD. So problems from differential geometries. Nowadays, the problems in differential geometry solved using PD. Okay. So anyway, okay. Okay. Thank you. We'll see in the next class, the Laplace equation. Thank you.
Thank you, sir.